Hey there, geology enthusiasts. Today we're diving deep, and I mean really deep, into the Earth's mantle. Strap in, because this is going to be a fascinating journey. First off, let's get our bearings. The Earth's structure is like an onion with layers. You've got the crust, which is what we live on. Then beneath that is the mantle. It's an enormous layer that extends about 2,900 kilometers down, and it makes up about 84% of Earth's volume. But what exactly is the mantle made of? The mantle is composed of silicate minerals that are rich in iron and magnesium. It's mostly solid, but it behaves like a very viscous liquid over long periods, allowing for the slow movement of tectonic plates. This movement is crucial for all sorts of geological activity. Now let's talk about the boundary that separates the crust and the mantle, the Mohorovicic discontinuity, or the MOHO. Discovered by seismologist Andrea Mohorovicic in 1909, this boundary is characterized by a sudden increase in seismic wave velocities. Why? Because the rocks below the MOHO are denser and more rigid than the rocks above it. It's like the Earth's very own speed bump. Moving deeper, we encounter another important boundary, the Gutenberg discontinuity. This marks the separation between the mantle and the core, located at about 2,900 kilometers below the surface. Unlike the MOHO, the Gutenberg discontinuity represents a dramatic change from solid rock to molten iron and nickel. Seismic waves slow down significantly here, giving us clues about the liquid outer core beneath. So why do these discontinuities matter? They help us understand the behavior of seismic waves, which in turn helps us map out the interior of our planet. This mapping is crucial for everything from predicting earthquakes to understanding the magnetic field generated by the core. But wait, there's more. The mantle itself isn't uniform. It's divided into the upper mantle and the lower mantle, with a transition zone in between, around 410 to 660 kilometers deep. This zone acts like a buffer, where minerals undergo phase changes due to the extreme pressure and temperature conditions. Think of it as the Earth's own pressure cooker. In the upper mantle, we find a partially molten layer known as the asthenosphere. This is where convection currents occur, driving the movement of tectonic plates. Above the asthenosphere lies the lithosphere, which includes the crust and the uppermost part of the mantle. This rigid layer is what breaks into tectonic plates. And guess what? The mantle isn't just about heat and pressure, it's also a treasure trove of information. By studying mantle xenoliths, pieces of the mantle that have been brought to the surface by volcanic activity, we can learn about the composition and conditions deep within the Earth. It's like getting a postcard from the depths. So the next time you think about the ground beneath your feet, remember that there's an entire world down there, teeming with activity and secrets waiting to be uncovered. The mantle is not just a layer, it's a dynamic, ever-changing part of our planet that holds the key to many geological mysteries. All right, that's a wrap for today's deep dive into the mantle. Keep exploring, keep questioning, and stay curious. Until next time, happy studying.